Welcome back, everybody, and in this lesson we're going to be discussing the generals of algorithms and an introduction into how and why we study algorithms. Now, we have many reasons to study algorithms. This is because an algorithm is basically a guaranteed way of solving a problem. Algorithms are so powerful because they allow us to make sure that if we have a problem and we have a correct and efficient algorithm, we can be guaranteed a solution within a real amount of time. This is extremely useful, as if you do solve a problem with a human, there's always a chance that they might have messed up. But by having an algorithm, we can make sure we're correct. This is different to other types of problem solving, where we don't necessarily know that we nailed everything. For example, a general thought process might work well in most cases, but it won't always work perfectly. An algorithm must work perfectly every single time. Now, there's also multiple ways to create an algorithm and multiple algorithms for each situation. Depending on the situation, you'll notice that there are either 2 or 3 algorithms or hundreds of possible algorithms. For example, sorting is one of the most common problems in computer science, and we've been developing algorithms for that since the 1970s. As a result, there's hundreds of sorting algorithms out there, but we need to make sure that we pick the best one for the situation. Now, this is extremely important because an algorithm is only a really useful algorithm if it works correctly, consistently, and is cost efficient. This means that, first of all, we need to make sure that the algorithm always works. This is the correctly and consistently part. Because if it doesn't, then we can't really rely on the algorithm. People rely on computers to be perfect. So when we put a computer when we solve a problem with an algorithm, we need to make sure that it works every single time, no matter what type of system you're using. Cost efficient is something people struggle with sometimes, but it basically means that our algorithm has to work within certain bounds. These bounds are the bounds of reality. We need to make sure that our algorithm finishes in a reasonable amount of time, space, and memory, because otherwise we don't really have a usable algorithm. An algorithm that either needs billions of dollars of computing equipment or takes 20 million years is pretty much as useless as having no algorithm at all. So we need to make sure we create algorithms and apply algorithms that fit well to the situation. Now, why study algorithms? Algorithms basically allow us to solve more difficult problems than the simple structures we've covered before. For example, let's say we needed to sort 2 billion numbers. First, we need to make sure that we have a sorting algorithm, because a sorting algorithm allows us to sort a large number of values. We can't sort 2 billion numbers by hand, because if we tried to do this, it would take millions of years. But we need to make sure we can sort our values today or within a reasonable amount of time. As a result, we need to make sure that we develop a useful algorithm that can work for this situation. Now, algorithms work very, very closely with arrays, loops, and control statements that we've covered before. This is because algorithms are basically tools that we use for every situation. Arrays, loops, and control statements are like a simple hammer. They can be used to nail in a nail, but on their own, they're not that powerful. Algorithms allow us to take these basic statements and these basic data structures and combine them and make more complex solutions. To continue the previous analogy, if we had a hammer, that would be like a control statement, but if we have a sorting algorithm, it's like being able to build a house, where the hammer is only one part of that house building. So an algorithm basically takes all of the previous ideas we've learned and combines them to make more powerful solutions. Now, we also have to make sure we pick the right algorithm. Many times, there's lots of different algorithms. For example, that sorting example, like I said, there's hundreds of sorting algorithms out there. So we need to make sure we pick a good algorithm for the situation. We also need to make sure we modify established algorithms for our problem. Many times, the algorithms that we are given only work for a certain number of values or only for a certain type of solution. We need to make sure that our algorithms work for every type of solution, because otherwise we're not really building a true algorithm. We're simply applying tools. But many times our problems won't be as cleanly defined as in a textbook, so you have to be adaptable to your algorithm. For example, with those 2 billion numbers, if we know they're all integer numbers, then we could use a very powerful sorting sort called radix sort, which could only take 20 minutes. But if we try to use a bad sorting algorithm like insertion sort, it might take millions of years. So we have to make sure we pick the right type of sort for the situation. In addition, we also have many restraints for every single algorithm. These restraints are basically what do we measure an algorithm by. The correctness part is part of every single algorithm. We won't discuss that because we assume that if we have an algorithm, it works correctly, consistently. These are the baseline cases, otherwise you don't even have an algorithm. But what determines one algorithm being better than another algorithm for the situation? In that previous example, time was the biggest test, and you'll notice that most of the time, we will place time efficiency as our most important thing. This is because time keeps marching onwards. We can't slow down time or buy more time in the same way we can for memory or space. So we need to make sure that when we create our algorithms, most of the time we're optimizing so that they take the least amount of time. Memory is also very important because many times we have large data sets. For example, those 2 billion numbers might not fit into your computer's memory. So we need to make sure that we have memory-efficient algorithms so that when we're working with large data sets, everything works cleanly and doesn't cause integer overflows or require a billion-dollar system. Remember, most of the algorithms we're going to cover will be targeted towards consumer systems. This means that they have to work on pretty much any computer. Now, tying into this is space efficiency. Space efficiency is most important for legacy systems. This is because today, space is very cheap, but in older times, you might only have a couple of megabytes or only a couple hundred of megabytes of storage. Whereas today we take terabytes of storage for granted, we need to make sure that our algorithms work as far back as possible. This is because we don't know what type of system our client is going to be using. Our client could be using a 1920s system, or they could be using a 2018 system. So we need to make sure we pick the right algorithm for the situation. Otherwise, we might have an algorithm that works fine for today, but our older client and the client that we're actually shipping our code to might not be able to use the algorithm. So make sure when you pick your algorithm, you pick the right algorithm for the situation. Hopefully you've enjoyed this lesson. In this lesson, we covered what is an algorithm, why do we study algorithms, and what do we measure algorithms by. Now, in the next lesson, we're going to be covering how to create an algorithm and what makes an algorithm good and what are the practices we're going to follow.